Hello and welcome to our video presentation and guide to an experiment all about understanding and seeing characteristics of Reynolds number in action. Now, before we start, it is important to know what Reynolds number actually is. And the dimensionless quantity actually characterizes flow patterns through properties in the fluid and the fluid's velocity. And it can be determined by the equation that I'm showing on screen right now. Now, onto the experiment. First thing that needs to be done is to drill a hole of a known diameter in the bottom of a plastic bottle with a screw-on cap, as I've done here. Next, you must fill the bottle full of room temperature water and secure the cap tightly. And no, it will not drip as long as the cap is on. And with the bottle full of water, you will secure it to the top of a very tall graduated cylinder, which will act as a catching apparatus. And the resulting setup should look something like this. Now, to get an idea of Reynolds number characteristics, we will use the screw top as a valve to allow atmospheric pressure to let the water flow from the hole. The first trial will consist of you unscrewing the cap as necessary until the flow appears laminar outside of the hole. Once you have, you will mark the position on the cap and the bottle with something like a magic marker. So that way we have a set position on the cap that will give us laminar flow consistently. And then the same must be done, but this time for turbulent flow, as I've done here. Now that you have set positions for both laminar and turbulent flows, you will use these consistently so that you can gather data and information on how long it takes for both laminar and turbulent flow to reach a specific volume of 250 milliliters using a stopwatch. I went ahead and timed a trial for both laminar and turbulent flows, and the amount of time it took laminar flow to reach 250 milliliters was about 54.2 seconds, whereas with turbulent flow, it only took about 23.8 seconds. Now, it will take multiple attempts of both laminar and turbulent flow so that you can get specific data across a mean average of times that it would take both of these flows to reach 250 milliliters. Once you've calculated the average for both of those flow positions, you will then use the number to plug into the equation for volumetric flow rate. So that way you can find it for both laminar and turbulent flows across the position. Now, taking that volumetric flow rate and the area of the hole you drilled in the bottle, you will get the flow velocity. Once we've gathered the flow velocity with the following equation, we can then plug it in to Reynolds number equation. Once we've characterized all the properties of the room temperature tap water we were using, we can get the Reynolds number of both our laminar and turbulent flows. And here's a little sample data of the numbers that me and my team came up with when we ran the trial of the experiment. Yes, this experiment very much does reinforce the properties and characteristics of Reynolds number that we've theorized and sought out in the real world. And I hope you've enjoyed this presentation. Thank you very much.